L'Hopital's rule. Our objective is to identify indeterminate forms and use L'Hopital's rule to find a limit. An indeterminate form of a limit is when the limit cannot be determined without additional work. Common types of indeterminate forms are 0 over 0 or infinity over infinity. Other types that we'll see are 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. When we use direct substitution when evaluating a limit and we get any of these expressions, it is an indeterminate form. We cannot determine the limit. The indeterminate form at C, if the functions f and g are each defined on an open interval containing C, then the quotient f of x over g of x is called an indeterminate form at C of the type 0 over 0 or infinity over infinity if the limit as x approaches C of the numerator f of x equals 0 and the limit as x approaches C of g of x, the denominator, equals 0. So both of these happen and we get 0 over 0. Or the limit as x approaches C of f of x equals positive or negative infinity, and the limit as x approaches C of g of x equals positive or negative infinity. If both of those things happen, we get the indeterminate form infinity over infinity. Either way, we cannot determine the limit without additional work. Previously, we've discussed ways to manipulate the expression to take the limit. Our additional work was factoring or rationalizing or using a special trig limit. Today we're going to talk about another way, L'Hopital's rule. Let f and g be functions that are differentiable on an open interval. C equals either a real number or infinity, and g prime of x, the derivative of the denominator, does not equal 0. If the result from direct substitution is the indeterminate form of the type 0 over 0 or infinity over infinity, then the limit as x approaches C of f of x divided by g of x equals the limit as x approaches C of f prime of x divided by g prime of x. Note that this is the quotient of the derivatives, not the quotient rule. Again, note this is the quotient of the derivatives. We're taking the derivative of the numerator, the derivative of the denominator. This is different. This is not the quotient rule. Note that L'Hopital's rule can be used multiple times for the same expression if possible, meaning if we keep getting the indeterminate form of the type 0 over 0 or infinity over infinity. Also, that L'Hopital's rule can be used for one-sided limits. Let's take a look at some examples. Identify each quotient as an indeterminate form of the type 0 over 0 or infinity over infinity. Then use L'Hopital's rule to find the limit. 1. The limit as x approaches 1 of x minus 1 divided by the quantity x squared plus 2x minus 3. I start with direct substitution, plugging 1 into the x. I get 1 minus 1 in the numerator, 1 squared plus 2 times 1 minus 3, and that yields 0 over 0. Notice I'm not putting an equal sign because 0 over 0 is not a value, and we only put an equal sign when we have a value. This is the indeterminate form, 0 over 0, which means I can use L'Hopital's rule to find the limit. So L'Hopital's rule says that this limit will be equivalent to the limit, as x approaches 1, of the derivative of the numerator, which is 1, over the derivative of the denominator, which is 2x plus 2. Now I try direct substitution again, 1 over 2 times 1 plus 2, and that makes 1/4. That is a value. I have found a limit. 2. Limit as x approaches 0 of the quantity 3 cosine x minus 3 divided by x squared. I start with direct substitution, plugging 0 in for the x. 3 cosine 0 minus 3 over 0 squared. Cosine 0 is 1, 3 minus 3 is 0, and 0 squared is 0. That's the indeterminate form, one of them that allows me to use L'Hopital's rule. So I'll proceed with L'Hopital's rule. The limit as x approaches 0, the derivative of the numerator is negative 3 sine x, since the derivative of cosine x is negative sine x, and the derivative of the constant 3 is 0, divided by 2x. Now I try direct substitution again. Negative 3 sine 0 divided by 2 times 0. Sine 0 is 0, and I end up with 0 divided by 0 again. This allows me to use L'Hopital's rule, so I do it again. The limit as x approaches 0, the derivative of the numerator is negative 3 cosine x, and the derivative of the denominator is 2. Now I try direct substitution, plug my 0 into the x, negative 3 cosine 0 over 2, cosine 0 is 1, I get negative 3 halves. That is a value. I've determined my limit. Number 3, the limit as x approaches infinity of e to the x divided by the quantity 5x squared minus 9x. I start with direct substitution, but when I think about e to the infinity, what I really want to do is think about the graph of y equals e to the x, which looks like this, and think about what happens as x approaches infinity, as x gets very large, or moving to the right, and the graph increases without bound. So my numerator is going to infinity, increasing without bound, and in the denominator I plug in very large numbers, and the denominator is also increasing without bound, and this limit of the numerator is infinity, the limit of the denominator is infinity, so I have the indeterminate form infinity over infinity. I can use L'Hopital's rule, so this limit will be equivalent to the limit as x approaches infinity. The derivative of the numerator, e to the x, is e to the x, and the derivative of the denominator is 10x minus 9. Now once again, my numerator, because it's still e to the x, will end up yielding a limit of infinity. The denominator, as I plug in very large numbers into x, I get infinity there as well. The indeterminate form again, infinity over infinity, allows me to use L'Hopital's rule again. The derivative of the numerator, still e to the x, and now the derivative of the denominator is 10. My numerator will be growing without bound, while my denominator is staying constant. Therefore, this limit is infinity. That is not indeterminate. The limit of this function is infinity, which means this function is increasing without bound. This is a valid answer for my limit. Number 4, the limit as x approaches infinity of natural log x divided by x. Similarly to the exponential function, I'd prefer to think of what y equals natural log x graph looks like. So we'll do a quick sketch of that, even if it's just mentally. And we see that as x gets very large, which is where we're looking, that this graph also continues to increase. Notice it doesn't increase as quickly as the exponential function. It is growing at a slower rate, but it is still always growing, or the function is approaching infinity. So let's look at the numerator, infinity, and the limit of the denominator, also infinity. So we have infinity over infinity. That indeterminate form allows me to use L'Hopital's rule. So I can set this equivalent to the limit as x approaches infinity, of the derivative of the numerator. The derivative of natural log x is 1 over x, and the derivative of the denominator x is 1. Now what I could do is rewrite this a little bit simpler before I try to evaluate the limit, so I'll do that. This is the same as saying the limit as x approaches infinity of 1 over x, and as our denominator increases without bound while the numerator stays the same, this limit is 0. This is a valid answer. I've found my limit. Thanks for watching.